Today I'm going to talk about LeetCode question number 230, kth smallest element in a BST. Given the root of a binary search tree and an integer k, return the kth smallest value, which is one indexed, of all the values of the nodes in the tree. Okay, so this is a binary search tree where values on the left of the root are smaller than it, and all the values on the right of the root are smaller, are bigger, I mean. Okay, and we want the kth smallest value. So if k is 1, we want the first smallest value, which is obviously 1 here. And here, k equals 3, we want the third smallest value, which is this guy here. So how can we go about this? Well, it's pretty easy. We can do in order traversal of the binary search tree and store all our elements in an array. Okay, and from that array we can determine the kth smallest element. So k is 1 index, so we get the k minus 1th element in the array here. Okay, and in order traversal is basically where you visit the left child, then the root, then the right child. And in a binary search tree, this basically means we get the tree back in, we get the iterated tree back in sorted order. So if we did an in order traversal on this, so we have our root here, but first we gotta visit the left child, okay, here. So we're at this node, but first we also gotta visit this guy's left child. It turns out it doesn't have left child, okay, so we add this to our result, okay, and then we look at the right child, and the right child is 2, so okay, and then we come back up here. Okay, and then we add 3, because remember it's left, middle, right. Okay, we already looked at the left, now we looked at the middle, now we're going to look at the right. And it's 4. Does 4 have a left child that we can look at first? Nope, so we're going to add 4. And does 4 have a right child we can look at next? Nope, so we're at the end here. And this is our in order traversal result. Okay. Instead of doing in order traversal recursively and add in all the elements in an array here, where this array size becomes n, where n is the number of nodes in the binary search tree, we can also do this iteratively. So instead of in order traversal recursively, we can do it iteratively, and we get the result from there. And if we do it iteratively, then there's a chance we don't have to explore all the nodes. If we find the third smallest value, then we can just stop there, okay? If the node is like 500, if the tree has like 500 nodes and all we need is third smallest value, then once we find the third smallest value, we could just stop there. We don't have to traverse all 500 nodes in the tree. How do we do this? Basically, we iterate through this traversive. We iterate through the tree not recursively, iteratively, and we simulate stack behavior using an array. Okay, so this is our stack here, and what we're going to do is just like regular in order traversal of recursively, we're going to explore all the left children first. Okay, but before we explore the left children, we got to remember that we're going to come back to this 3. We got to remember we're going to come back to this 3. So we're going to add it to our stack as a reminder to ourselves that we got to come back to it. Okay, and then we look at the left child. Okay, 1, but we got to explore 1's left subtree. Okay, so we added our stack to remember. Okay, and now it turns out 1 does not have a left child. Okay, great. So remember in the order traversal, it's left, and then root, and then left, and then middle, and then right. Okay. So since we don't have a left child to explore, we can just look at this value here, the middle one. So we pop it in the stack. Okay, and append it to our result. Okay, and notice the element we just popped is the first smallest value. Okay, it's the first smallest value. Let's do this to get all the way to the, yeah, and so if k is equals 1, we found the first smallest value. Okay, let's keep going until we find the third smallest value. Okay, so we just popped 1, and our current node is 1, and now we want to explore the right subtree. Okay, so then we're at the right subtree here. We already we already saw 1, so we don't need to put it back in our stack. Now we're going to look at the right subtree. Okay, and now we're at the right subtree here. We want to try to explore the left subtree first, so we add it to our stack. So it turns out there's no left, it's null, so we pop it now, and we just got our second smallest value, okay, which is 2. Okay, and now that we're done with this, we come back up, okay, and since it's left, middle, right, we look at this node here. Okay, now we pop it, and we add 3. Okay, now we just got our third smallest value, and this is what we were looking for, the third smallest value here. So basically, every time we pop from the stack, we get our nth smallest value. Okay, so if we pop our first element from the stack, we get our first smallest value. We pop a second element from the stack, we get a second smallest value, etc. Okay, and that's how we're gonna do this in our traversal iteratively to find the kth smallest value. Okay, it saves on space. Worst case, we have O of n space, you know, just in case the node is like 500, in case the tree is 500 nodes big and we want the 500th smallest value, then obviously we have to explore the entire tree. But this is a better memory optimization, and for time-space complexity, it's O of n because we only look at each node in the tree once. Okay, now to code this up, so what we're going to do is define our stack here. Okay, and our current node, which is going to be the root. And what else are we going to do? Or we're going to have a counter, which is initially going to be 0. Our pop counter, and it's going to keep track of how many times we've popped from our stack here, and if it matches k, if we popped k times from the stack, then that's k's smallest value, and we return the current node's value. Okay, so I'm just gonna write up an iterative in order traversal. So while current is not none, or the length of stack is not equal to 0, what we're gonna do. So while the current node is not none, and or the stack's length it still has elements in it, what we're going to do is, while current is not equal to none, stack up and current, and we're basically, what we're doing here is exploring the entire left side, and I'm pushing it to our stack here. Current equals cur.next, okay. And then after we explored our entire left side here, we know we've done it, we're finished exploring our entire left side when current is none. Okay, that means we're here, like the left child of 1 is none. Okay, and what we want to do is pop from the stack. And then increment pop to counter. If counter equals k, then return current dot val, or else current dot val equal to oops, I mean current is equal to current dot next. Okay. So yeah, we're just going to keep exploring the left until we reach null. Okay. And once the left subchild of a node is null, that means we can look at this middle child here. So that's what we're going to do, stack.pop. Okay. And at this point, we would have popped like the first smallest node. And then what we're going to do is, what we're going to do is once we explored the middle node, we're going to explore the node's right subtree here. So that's what we're doing, cur equals cur.right. And similarly up here, in the next iteration, for that right node, which is non-existent here, but imagine it's here, we're going to explore entire left. So you can't anymore. Pop, look at the middle node value, and then look at the right child. Okay. So now I'll try running the code, I'll try compiling it. Not next. Okay, and I'll try submitted. Okay, great, thanks for watching.